Hello, this is Linda Lee. I'm going to introduce our paper, SimNet, Accurate and High Performance Computer Architecture Simulation using Deep Learning. This work is done with my colleagues from Brookhaven National Lab and collaborators from Stevens Institute of Technology and Laboratory for Physical Sciences. First, I will introduce the background for computer architecture simulation. Computer architecture simulators are essential to computer architecture research and engineering. They are used for data space exploration as well as to evaluate new ideas. A typical computer architecture simulator will simulate different architecture components, instructions, and their interactions. This figure shows a two-stage processor here. One is the ECU stage, one is the execute stage. We'll show how two instructions execute in these two stages. We have two instructions, one add instruction, one XOR instruction. Because there are dependencies between them, we'll need to execute the add instruction first in the integer execution unit. After this instruction finishes, we can execute XOR instructions. So this traditional type of simulator suffers from high computational costs. The state-of-art Gen 5 simulator executes at a speed of several thousands of instructions per second. And we will need weeks, even months to simulate real-world workloads at this speed. Because this current event simulation is highly irregular and difficult to parallelize, so their performance didn't get much improved in the recent years. In this paper, we explore a new path, which is to use machine learning for computer architecture simulation. Machine learning has shown great success in many domains, essentially because machine learning models are excellent function approximators. For example, in the natural language processing domain, machine learning models are used to map between words and their semantical meanings. Another advantage of machine learning is highly regular and parallel. And the modern accelerators like GPUs and TPUs are well optimized for machine learning. So there could be a performance advantage of machine learning-based approach. In this paper, we propose the first machine learning-based computer architecture simulator, which we call SimNet. In this presentation, first of all, I will introduce the methodology of SimNet. Then I will evaluate the accuracy of our machine learning-based simulation approach. At the end, I will introduce the performance of SimNet. Let's start with the methodology of SimNet. The process of simulation is essential to predict instruction latencies. From the simple example we showed before, we can see the latency of an instruction is decided by its own properties, like its operation types, etc., as well as the current architecture component states. Like in the example before, we show the states of the ECU unit as well as the function units. And the architecture component states is decided by the previous instructions through the simulation process. So from this figure, we can see that the latency of an instruction is essentially decided by its own properties as well as previous executed instructions. Based on that, we propose a machine learning-based latency predictor to replace the simulation process. It will take the previous instructions as well as the current instruction property as input and to output the predict latency of this instruction. So first, let's see how how do we construct the input features for this machine learning-based predictor. I introduced before, the first part of the input should capture the instruction properties, which include operation type, register indices, etc. And the second part is the prevent instruction. We further categorize them into two classes. One is called context instruction here, which include instructions that are still under execution. These instructions decide most architecture component states, like the function unit, ECU unit we showed before. And the total number of context instructions is limited. Usually it's a couple hundred in modern processors. So we directly have these context instructions as the input features. The other part of prevent instruction is the instructions that are already retired. All these retired instructions, they can impact the cache and branch predictor states. Because there are too many retired instructions, it's infeasible to directly use them as the input features. Instead, we propose to use simplified simulation results to capture their impact. Particularly, we want to capture the impact of cache and branch predictor. We use cache access levels to capture the cache impact and use branch prediction results to capture the branch predictor states. More details can be seen in our paper. So with these three different set of input features, we are ready to predict the latency. All of them fit into a machine learning model. And in this paper, we evaluate a wide range of machine learning models, include deep convolutional neural nets, long short-term memories, and transformers. And the output of this model has three latency. First one is fetch latency, which indicates the number of cycles to fetch an instruction after the previous instruction. They also output execution and stall latency, which indicate how many cycles an instruction need to finish. So to train such a model, we modify the state-of-the-art Gen 5 simulator to get all the training data. Particularly, we use 4 spec CPU 2017 benchmarks for training and the other spec 2017 benchmarks for simulation. Note that we can also generate training data from other sources. We train our models on NVIDIA DGX A100 system, which has 8 GPUs. We use PyTorch to train our model and the add-on optimizer. For each model, we train 200 epochs and using a validation data set. Once the model is trained, it can be used to simulate any program. With this proposed machine learning-based latency predictor, we can simulate the performance of our application. Our application, we use all its instructions as an input trace. And each time we fetch one instruction from the input trace. We use history context simulation to simulate caches and branch predictors to get the impact of the retired instructions. After the machine learning model makes its prediction, using its fetched latency, we use a unit called clock management to record the total number of simulated cycles. Using the predicted execution and stall latency, we manage the active instructions and their features, which will be used as part of input features for the later predictions. And we go through every instruction in the input trace. At the end, we'll get a total number of cycles to execute this application. Then I will introduce the accuracy of our machine learning-based simulation approach. First, I will evaluate instruction latency, prediction accuracy. The figure left shows the prediction error, and the figure in the middle shows the computation complexity of different models. For SimNet, we evaluate 4 models. C3 is a 3-layer convolutional net model. Also evaluate a 2-layer LSTM model and a 6-layer transformer model. In the end, we evaluate RB7, which is a 7-layer residual convolutional net model. Besides SimNet, we also compare with SIMO, which is a basic block latency predictor using a 4-layer LSTM. From these figures, we can see that SimNet significantly outperforms SIMO in both accuracy and the computational overhead. Among different SimNet models, RB7 model achieves the best prediction accuracy using a reasonable computational overhead. Then we evaluate the application simulation performance. So the figure here shows the simulated cycle per instruction CPI of all spec CPU 2017 benchmarks. From this figure, we can see that SimNet actually predicts application performance of all benchmarks. Among different SimNet models, the RB7 model achieves the best accuracy with an average error of 5.6%. In the end, we also evaluate application behavior variation under SimNet. So these figures shows how the CPI changes over time during the simulation of 100 million instructions under Gen 5. We can clearly see different applications have different execution phases. The red line shows how the SimNet simulate these benchmarks and how CPI changes under SimNet RB7 model. We can see the curves of SimNet closely resemble the curves of Gen 5. They indicate that SimNet can capture the application behavior as well as Gen 5. In the end, we propose a parallel GPU-based simulation to accelerate SimNet. The key idea here is to partition input instructions into multiple subtraces. And for individual subtraces, they are simulated in parallel to utilize the high throughput GPU batched inference. Besides GPU parallelism, we also use CPU parallelism in SimNet. Particularly, we use CPU multithreading to process different subtraces. This figure briefly shows the simulation throughput of SimNet and a different number of GPUs. The SimNet performance increased almost linear with the number of GPUs. Using 8 GPUs, SimNet achieved about 7 to 76x speedup compared with Gen 5. SimNet also achieved higher power throughput, higher power efficiency compared with Gen 5, thanks to GPUs' better computation efficiency. So in summary, we propose the first machine learning-based computer architecture simulator, SimNet. Particularly, we propose to use a machine learning model to predict instruction latency. And we propose a set of input features for such predictions. Then we can calculate the application performance using all predicted instruction latencies. We evaluate the accuracy of SimNet through instruction prediction accuracy, application prediction accuracy, and application execution phases. We can see that SimNet achieves excellent simulation accuracy in all three cases. Among different SimNet models, we show that convolution net models are more accurate and efficient than LSTM models and the transformer models for computer architecture simulation. In the end, we show using state-of-the-art GPUs, SimNet can achieve significantly higher simulation throughput. I have open sourced our code on GitHub, and please feel free to contact me with any questions or comments. Thanks for listening.